Vanakkam my dear students. In this video we are going to see exercise 2.1 sums. First one, find all positive integers when divided by 3 leaves the remainder 2. So we are going to find the positive integers when the integer is divided by 3 leaves the remainder as 2. Okay, so here let the required positive integer we are going to assume as a. Okay, so given that number, that is a is divided by 3 leaves remainder 2. So by Euclid division lemma already we know we have a equal to bq plus r, where 0 is less than or equal to r is less than modulus of b. So here divided by 3, that is the divisor. So you have to write a equal to bq. They given the remainder as 2, so r value as 2. So where q is greater than or equal to 0, because they given positive integers. So q must be greater than or equal to 0. So q we are taking greater than or equal to 0 means 0, 1, 2, 3 and etc. Now we are going to substitute this 0, 1, 2, 3 in this equation, then we will get the required numbers. So 3, so q value first we are taking 0. So 3 into 0 plus 2. Come on, next we are substituting 1. So 3 into 1 plus 2. Next we are substituting 2. So 3 into 2 plus 2. 3 into 3 plus 2 and so on. So 3 into 0 you will get 0. 0 plus 2, 2. 3 ones are 3. 3 plus 2, 5. 3 twos are 6. 6 plus 2, 8. 3 threes are 9. 9 plus 2, 11 and so on. Therefore, the required numbers are 2, 5, 8, 11 and so on. If you divide 2 with 3, so 3 zeros are 0. So we will get the remainder as 2. So 5. 3 ones are 3. So what is the remainder? 2. So if you divide these numbers into 3, you will get the remainder as 2. Okay. So next one. Fourth sum. When the positive integers a, b and c are divided by 13, the respective remainders are 9, 7 and 10. Show that a plus b plus c is divisible by 13. So here the one number a, if it is divided by 13, leaves the remainder 9. Is it clear? If a is divided by 13, leaves the remainder 9. If b is divided by 13, leaves the remainder 7. If c is divided by 13, leaves the remainder 10. We are going to show that a plus b plus c is divisible by 13. So a plus b plus c is divisible by 13 means the remainder should be 0. Okay. So given the positive integers a, b and c are divided by 13, leaves the remainder 9, 7 and 10 respectively. So by Euclid division lemma already we know we have a equal to bq plus r, where 0 is less than or equal to r is less than modulus of b. So a equal to 13q1 plus 9. We are using Euclid division lemma here. Using that. Then b equal to 13q2 plus 7. C can be written as 13q3 plus 10. We are going to add these three. A plus b plus c equal to 13q1. So a value 13q1 plus 9. Right. Next b 13q2 plus 7. C is 13q3 plus 10. So 13q1, 13q2, 13q3. In this you can take 13 as common. So I can write q1 plus q2 plus q3 plus 9 plus 7 plus 10. Add these three numbers, you will get 26. So in this 26 can be written as 13 2s are 26, isn't it? So in both these two you can take 13 as common. So what will you get? q1 plus q2 plus q3. Here you have 2, you know. So plus 2. Now I am assuming this q1 plus q2 plus q3 plus 2 as q. I am assuming like this. Okay, so we will get 13q. Here there is no remainder, isn't it? So if it is in the form a equal to bq plus r, here the remainder you can write it as 0. So where q equal to q1 plus q2 plus q3 plus 2, m is a positive integer. Here I took q. Q be a positive integer. Therefore, A plus B plus C is divisible by 13. How we are saying it is divisible by 13? Here we got the remainder as 0. So, it is a multiple of 13. So, therefore, A plus B plus C is divisible by 13. Okay, did you understand this? So, move on to fifth one. Prove that the square of an integer leaves a remainder either 0 or 1 when divided by 4. So here we are going to prove, we are going to square a number, that number leaves a remainder either 0 or 1 when divided by 4. So if you divide a square of a number with 4, the remainder should be either 0 or 1. We are going to prove. So all the integers here must be either even or odd. They didn't given, they given only integer. So that integer may be even or odd. So if it is an even, then A equal to 2Q. If it is odd, then A equal to 2Q plus 1. So in case 1, we are taking A equal to 2Q. Square of an integer they ask no. For that we are squaring now. A square equal to 2Q whole square. What is 2Q whole square? 4Q square. So here the remainder is 0, isn't it? It is a multiple of 4. So when it is divided by 0, the remainder is, so when it is divided by 4, the remainder is 0. Okay, next case 2, odd number. So A equal to 2Q plus 1. We are going to square this. A square equal to 2Q plus 1 whole square. So it is in the form A plus B whole square. What is A plus B whole square formula? A square plus 2AB plus B square. If you split now, you will get 4Q square plus 4Q plus 1. So in these two terms, I am going to take it out common as 4Q. If I take now, I will get Q plus 1. Let's write this plus 1 as it is here. Okay. So now I am assuming this Q into Q plus 1 as M. Okay, so A square equal to 4n plus 1, where m equal to q into q plus 1 is an integer. So here the remainder what you got here? 1. 1 is the remainder when it is divided by 4. In the 4, here you have 4 you know. Therefore, the square of any integer leaves the remainder either 0. If it is an even number, it leaves the remainder as 0. If it is an odd number, it leaves the remainder as 1. Okay, so either 0 or 1 when divided by 4. Is it clear, my children? Move on to third sum. Prove that the product of two consecutive positive integers is divisible by 2. Now we are taking two consecutive positive integers. Whether you are going to check, you are going to prove that is divisible by 2. So what is divisible by 2? Now definitely we will get the remainder as 0. Okay, so let I am taking n and n plus 1 be consecutive positive integers. B equal to 2. How we are writing B equal to 2? We are divisible by 2 you know. So the divisor is 2. So we are taking B equal to 2. So by Euclid division lemma, we have A equal to BQ plus R, where 0 is less than or equal to R is less than modulus of B. N equal to 2Q plus R. B value is 2 plus R, where 0 is less than or equal to R is less than modulus of B. Modulus of B now, what is the remainder then? 0 and 1. 0 comma 1. So now I am writing n equal to 2q plus 0. 2q plus 0 will get 2q. Then n equal to 2q, remainder again taking plus 1. So n equal to 2q plus 1. I am substituting the remainder values in this equation. I will get n equal to 2q or n equal to 2q plus 1. So case 1. Now I am taking this n equal to 2q. If n equal to 2 by consecutive numbers, integers what I take? N into n plus 1 you know. So n plus 1 will be 2q plus 1. Product, they ask product of two consecutive integers. Product means you have to multiply. So n into n plus 1 equal to, here you have 2q, n plus 1 value is 2q plus 1. So now I am assuming this q into 2q plus 1 as m. So I got 2m. It is a multiple of 2, isn't it? Every multiple of 2 must be divisible by 0 and the remainder should be, it must be divisible by 2 and the remainder should be 0 you know. So here they write that m equal to q into 2q plus 1 and m is positive. Therefore n into n plus 1 is divisible by 2. Okay, next case 2. So case 2, n equal to 2q plus 1. What will be then n plus 1 plus 1? 2q plus 1 plus 1. 1 plus 1 you will get 2. So n plus 1 value is 2q plus 2. So n into, that is 2q plus 1 into 2q plus 2. Now we are going to multiply these two. 2q into 2q, 4q square. 2q into 2q, 4q. Again 1 into 2q, 2q. 1 into 2. 2. So 4q plus 2q will get 6q. So in these three terms I am going to take 2 as common. If you take now you will get 2 into 2q square plus 3q plus 1. So here also 2q square plus 3q plus 1 I will take it as p. Here you got 2p. It is a multiple of 2. Definitely it will divisible by 2. So where p equal to 2q square plus 3q plus 1 and p is positive. Therefore n into n plus 1 is divisible by 2. Therefore if we take n equal to 2q, it is divisible by 2. If n equal to 2q plus 1, it is also divisible by 2. Therefore the product of two consecutive prime numbers is, two consecutive positive integers is divisible by 2. Next we are going to see 8th one. If D is the highest common factor of 32 and 60, find x and y satisfying D equal to 32x plus 60y. So using division algorithm, already I told division algorithm. So we are going to find the HCF of 32 and 60. So first you have to take greater number as divided. 60 equal to 60 can be written 32 into 1. The remainder will be 28. Again you have to take 32 as divided, 28 as divisor. So 32 equal to 28 into 1 plus 4. So next step, take 28 as divided, 4 as the divisor. So 4 7s are 28, you will get the remainder as 0. So you have to stop here. So what is the divisor in this step? That is the HCF of the given two numbers, isn't it? So therefore HCF of 60 and 32 equal to 4. So they given D is nothing but the HCF of 32 and 60. D equal to 32x plus 60y. So D value we found as 4. So 4 equal to 32x plus 60y. So now we are going to have two variables now. So we are going to check with trial and error method. That is x equal to 1, y equal to 1. If you substitute now you will get 60 plus 32, 92 you will get. So like that if you check means when x equal to 2 and y equal to minus 1, it will satisfy the given equation. Check here, 4 equal to 32 into 2 plus 60 into minus 1. So 32 into 2 you will get 64, 60 into minus 1 minus 60. 64 minus 60 will get 4, 4 equal to 4. Therefore, so x equal to 2, y equal to minus 1 now, that it satisfies the given equation. So that the x value is 2 and y value is minus 1. Is it clear? So next move on to 9th one. When positive integers divided by 88 gives the remainder 61. When a positive integer is divided by 88, it gives a remainder as 61. What will be the remainder when the same number is divided by 11? So the same number is going to divide by 11 now. So what will be the remainder we are going to find? Okay, we doesn't know that number, positive integer. So let the positive integer be n. We are assuming that a positive integer as n. n equal to, if it is divided by 88, leaves the remainder 61. How to write this? n equal to 88p plus 61, where p is an integer. n equal to 88p plus 61, I am going to write it as 55 plus 6. Okay, so this 55 I can written as 11 into 5. Why you are writing like this? Means here they asked to divide it by 11, no. So you have to write multiples of 11. That's why we are writing 61 as 55 plus 6, 51 as 11 into 5. Okay, so 88 can be written as 11 into 8, isn't it? So in both these two terms, you can take 11 as common. What is the remaining here? 8p plus 5 plus 6. So it is in the form. So now I am going to assume 8p plus 5 as q. Okay, so 11q plus 6. So it is in the form a equal to bq plus r. So what is the remainder then? 6 is the remainder. Is it clear? So when the same number 10 is divided by 11, the remainder will be 6. That will be answer. Okay. Next, 10th one. Prove that two consecutive positive integers are always co-prime. We are going to prove that two consecutive positive integers are always co-prime. So co-prime means the HCF of two co-prime numbers is 1. If you prove that HCF of two consecutive integers is 1, then automatically the integers are co-prime. Okay. So let the two consecutive positive integers be n and n plus 1 I take here. So always n plus 1 will be greater than n, you know. So I am going to find the HCF of n plus 1 and n. So I can written greater number n plus 1 equal to n into 1 plus 1. Isn't it? So in here remainder I got 1. So you have to find HCF now. The remainder should be 0. Here the remainder is 1. So you have to proceed in the next step. Next step you have to take n. N equal to 1 into n plus the remainder will be 0. That only I wrote here. N equal to 1 into n plus 0. Here the remainder is 0. So you have to stop. Now what is the HCF then? This 1 is the HCF of n plus 1 and n. So HCF of n plus 1 comma n equal to 1. Therefore HCF of two consecutive positive integers is 1. If the HCF is 1, then the two consecutive positive integers are co-prime. Therefore two consecutive positive integers are always co-prime.